generate geometry. We also have the other parameter tree mean of so the parameter depend on the program. Program will apply different parameter depend on program you choose. Okay, each program will have different normalization. Now, when we have the normalized data or normalized count, we move to expression level, identify expression levels. And as you see above, the number of bits of count marked into biological feature interest, that means gene or transcript or exons, consider linear related to the abundance of the target feature. So depend on the number of bits here, we identify how much gene expressed, Very simple principle in the RNA sequencing technique. How to identify expression levels based on number of bits. And number of bits here related to the abundance of target feature, that means the gene expression level. That's the number of bits. Microarrays. Compared with microarrays, abundance of this sequence functional fluorescence level, so based on color intensity. You remember previous part explained about microarrays, and based on hybridization process. One based on color intensity, one based on number of bits. Up to now, we based on number of bits identifies expression level only, not yet differential expression or not. Because we want to know gene expression between two samples different or not. So that's why you have to move to differential expression. A gene declare differentially expressed if an observed different or gene in rich count between two experimental conditions statistically significant. Okay, also have perform statistical tests. You have to perform statistical tests. The results based on normalized parameter show you the expression level only, not yet confirmed difference. Okay, we have to go with the statistical test to see the difference. Statistical tool needed to make such decision by studying count probability distribution. And the statistical test depends on experimental design. Based on comparison, only two experimental conditions. Normally, we set up experiments with the control. Okay, with the control, so we compare two conditions, normally two. In case many, more than two conditions or group. And then that wise, we will have different samples within the same condition. The first one we call technical replicates, and the second one biological replicates. And in lecture 2, I already explained technical replicates and biological replicates. I think this one I already explained. Okay, technical replicate and biological replicate. We need replicates for statistical tests. Okay, it's for statistical tests. Differential gene expression methods. We also have programs performed for use to identify differential gene expression. I use these sets. An example, we have many programs, but we use this one. reset to.
To where?
Example of the noise signal distribution will compute the change in expression of each gene between two experiments and noise. That means distribution of change expression value when compare replicates. Compare replicates if between replicate any different remove it we got noise. And then at the end we have differential expression comparing signal and noise to determine differentially expressed changes. So this program very simple, just look at the signal distribution and also identify the noise distribution and the noise distribution based on replicate, data replicates. And merge between them, we have differential expression here. Okay, so the first one, distribution and the noise, and merge between them, we have the red one, that's the differential expression. How to evaluate the gene expression difference among samples? The first one, for the level, gene expression level, we base on log2 fold chain. Okay, log2 fold chains. After normalize counting, the program also calculate this one, log2 fold chain, to know higher expression or lower expression depending on you set up the value 1, 2, 3. Okay, if larger than 1, for example, you set up 1, less than 1, that means up regulation. Smaller than minus 1, down regulation. That about expression level only, not yet confirmed. You need to confirm by statistical tests. And in bioinformatics, we don't apply p-value. You study statistics, you know p-value. Here, we apply corrected p-value. The first one is about fold chains. Fold chains calculates supply ratio of the difference between the final value and initial value, or between the value of sample A and value of sample B. Okay? If you study only one sample, you look at the final value compared with the initial value. In case you compare two samples, you log 2 expression the fold chains. Log 2 of 2 equal 1 and log 2 of 0.5 equal minus 1. I already explained for the log 2 fold chains. Now, log 2 as you calculate fold chain measure the up regulate or down between samples. And why we apply log 2s? Log 2 measure data more close to the biological detectable genes. Okay, why we apply log 2? And many programs now apply this one, log 2 fold chain. But the full name, corrected p-value or p-adjust. Okay, p-adjust or q-value, the same thing. Remember that. I don't remember exactly, but I remember one question for me for exam here. Sorry, final exam. Will be final exam. The same thing, p-adjust or never we say corrected p-value very long, normally we call p-adjust. We say p-adjust that enough. After apply multiple statistical hypothesis examination on p-value. So that means here more significance. P-adjust already have p-value and program continue applying multiple statistical hypothesis examination on p-values. So higher than our original p-value, more efficient in control from positive. So So that's why we have to apply PHS to control point velocity, Point velocity, that means not express differentially between two samples, but you apply p-value maybe have solution different. Okay, so that's why we have applied PHS. Very acceptable threshold range for differentials, no between. That means it's up to your data. You should set up high or low. 1, 2, 3. It's up to you. It's up to you. And then here I show you the whole flow chart, how to study gene expression. But this one not yet published. And also show you the program to run. We start with the manual sequencing. Okay, here we finish sequencing and then apply program PACQ-C to check the quality. We apply three more methods to remove poor qualities and then continue. You ignore this one, we go to the second and the third column. I will explain this one later. And then the first step, assembly. And the assembly is we can perform with how many approach? 2. The first one, so this one link with. So what difference between 2 here? Anyone can see the difference? 1 and 2. So this one assembly, this one marking before assembly. Okay, so here, if marking before assembly, it means what? Reference based assembly, remember. Reference based assembly. The other name for reference based assembly. Because we based on the reference, but the reference is genome, so we have the other name, genome guided assembly. Okay, genome guided assembly. So this one applies to assembly approach. The first one's genome guided assembly, and the second one de novo. That's right, de novo assembly. Okay, and when we have transcriptome here, the assemblies, we move further with annotation. Before annotation, we have to check the quality, so that's why bus go. Okay, bus go, and then move to annotation. Several annotation here. The first one, last GO term interval scan. Okay, and then when we have transcriptome available, now we move to quantification. We study track quantification. In quantification, marking the program OT2 for the marking and counting ASEAN. Okay, ASEAN for counting. And after counting, we have insect to identify differential gene express, differentially expressed genes. Okay, so two here, very simple. And we also have the other approach for quantification. Here, the marking and also counting. This one mark directly to the reference if the reference available. This one based on the new assembly. Here, mark to the genome available. So for quantification, we have three approaches. The first approach, mark directly to the reference if reference available. Here, two new assembly, and two new assembly, one based on genome guided assembly, the other de novo assembly. So that's why you have three mapping approach. So this article will compare the effects of mapping between three approaches affect to the DEG. So DEG and DGE are different. DGE, E, that means expression. G, differential, okay? DGE, differential gene expression. DEG, differential gene express gene. So what difference between two terms? Here, specific gene. Identify which gene express differentially between same bond. Here, differential gene expression, that means the methods expression analysis. The GE analysis, the name of the methods. Okay, similar but different. One indicate gene, the other one expression analysis. Analyze to know which gene express differentially, differential gene expression. Okay, that's all for lecture today. And next week we have one more lecture, and then 2 more weeks of a presentation. And could I remind you, you do course evaluation survey. I don't think it takes long time, but many students hesitate to do that. That's very important because we make the improvement of the course and also